Welcome everyone to today's Explainer. We are jumping right in today because we have a genuinely fascinating technical breakdown ahead of us. We're looking at a model that promises to finally bridge that incredibly frustrating gap between constrained hardware and our constant demand for high reasoning capabilities. We're putting Gemma for E4B through the ultimate lab test based on some fantastic hands-on data.
Okay, let's dive into this. Our roadmap for today covers the local LLM dilemma, the PLE architecture advantage, benchmarking on SBCs and GPUs, multimodal and FOSS integration, and finally, the reasoning limits and complexities. Let's get to it.
Starting with Section 1, the local LLM dilemma. Let's set the stage by looking at the core problem facing every single home lab enthusiast and self-hoster out there right now.
If you've spent any time running local models, you know exactly what I'm talking about. It's that frustrating hardware trade-off. On one side, you've got your tiny sub-7 billion parameter models. Sure, they fit perfectly on weak hardware like a Raspberry Pi, but the second you try running something complex, like hooking them up to an agent harness for your Docker socket, it just devolves into an absolute mess. We're talking massive hallucinations, infinite loops, or literally just a full-on system meltdown. Then, on the flip side, you have these incredible 35 billion parameter mixture of experts models. They are highly accurate, but they're massive clankers. You simply can't run them without heavy hardware, massive VRAM, iGPU offloading, and way more than 8 gigs of memory. So you're basically trapped between uselessly small and unattainably huge.
Section 2. The PLE architecture advantage. So, the crucial point is, how do we break out of this trap? Well, that is exactly the dilemma Gemma for E4B is trying to solve.
I'm going to geek out on the architecture for a second here, because this is the absolute secret sauce. Gemma for E4B uses something called Per-Layer Embeddings, or PLE. This architecture essentially grants a dedicated embedding table to every single decoder layer inside the model. Okay, so what does that actually mean for you and your setup? Basically, the model can access significantly more information without entirely monopolizing your system resources. It functionally reduces its effective parameters down to just 4.5 billion. It is incredibly lightweight. But, and here's the kicker, because of that PLE architecture, it actually retains the knowledge and reasoning capacity of a much larger conventional 8 billion parameter model. It punches way above its weight class.
Section 3. Benchmarking SBCs and GPUs. We know the theory sounds great, but how does it actually run? Let's transition right into the hard numbers from our objective lab tests across several different hardware tiers.
And this brilliantly illustrates the real-world impact of that architecture we just talked about. Look at a Raspberry Pi 5 with 8 gigs of RAM. Normally, a Pi is going to struggle to even load a 5 billion parameter model, let alone run one. But Gemma for E4B, it actually runs on it, generating about 3 tokens per second. Now sure, that's not blazing fast for everyday productivity, but the fact that a single board computer can run this level of reasoning at all, that is wild. But then you scale it up to an older workstation GPU, something like a GTX 1080, and suddenly we are flying at around 35 tokens per second. Throw a modern powerhouse at it, like an RTX 3080 Ti, and it nearly triples that, soaring past 100 tokens per second. It scales absolutely beautifully across whatever you've got.
Section 4. Multimodal and FOSS integration. Raw speed is fantastic, obviously, but we need to know how this model actually behaves in the trenches when you integrate it with self-hosted, free and open-source software tools. To really get the most out of Gemma for E4B, you've got to unlock its multimodal capabilities. Because remember, this isn't just text, it processes audio and vision too. If you are using llama-server, you'll want to boot it up using a few specific flags: --mmproj, --jinja, and --webui mp proxy. Using these lets you hook up a Docker MCP server, which acts as a bridge to expand its inference and management capabilities right directly into your environment.
Once you have it hooked up, the list of real-world successes is just genuinely impressive. It handles PDF summaries straight through the web UI without breaking a sweat. You can toss it images and ask for descriptions, and honestly, aside from it failing to recognize one really obscure app called Cage, it succeeds every time. Because we hooked it to the Docker socket, it can pull new images and check your environments. It natively works beautifully with Open Notebook and Blinko for summarizing your notes. It's also highly effective at processing RAG queries, retrieval augmented generation, where it expertly filters out unnecessary source information to give you just the relevant details. It auto-generates tags for Crockheap and Paperless AI containers. It even helps you troubleshoot long, messy server logs. And incredibly, people are actually using this tiny model offline to execute complex wargaming projections, mapping out multi-month geopolitical and economic scenarios. It is an absolute workhorse.
Section 5. Reasoning limits and complexities. As much as we love a lightweight powerhouse, we have to stay objective here.
Let's take a hard look at the model's actual limitations.
So while it can definitely pull images and check environments, Gemma for E4B completely fails at the really heavy lifting deployment stuff. When you task it to actually call container creation tools from the Docker MCP server, or if you ask it to write full Ansible playbooks, it outputs malformed code with multiple errors. If you compare this to a bulky 35 billion parameter model like Qwen 3.6, which can spin up a fully functional container using just an image name, Gemma for E4B just falls flat. It simply doesn't have the vast context capability needed for high-level automated deployments.
Furthermore, if you're looking for a flawless brain for your smart home, you might want to look elsewhere. When tested as a conversational agent for a home assistant server, it really struggles with ambiguity. It frequently fails to select the right smart device if your commands are even slightly vague. More importantly, when you try to build out complex automation chains, it consistently messes up the if-then conditional logic. It's a fantastic assistant for sure, but it is definitely not a zero babysitting automation agent.
Let's move to how this builds into an actual, practical deployment strategy despite those limits. The true beauty of this PLE architecture is that it revives dead hardware. Step 1, you can literally dust off a decade-old laptop sitting in your closet with an old GTX 1060 in it. Step 2, apply a little bit of LXC GPU pass-through wizardry in your hypervisor. And step 3, suddenly you have deployed a highly capable, completely offline LXC hosting workstation powered entirely by Gemma for E4B. No, you aren't replacing your massive models for complex coding, but you are creating an incredible, lightweight daily driver for quick inference, note tagging, and document reading.
Which brings us to the ultimate takeaway for today's explainer. The barrier to entry for highly capable multimodal AI has fundamentally dropped. The game has changed. So I'll leave you with this. Looking around at the idle hardware you probably have sitting around your house right now, how will you utilize these lightweight PLE architectures in your own setups? It's time to start experimenting. Thanks for joining me on this deep dive, and happy self-hosting.